This video is about the difference between temperature and heat. So at the beginning of the video, we're going to talk about several different vocabulary words and what they mean, and then towards the end, there is math involved with this. So if you don't have a calculator, you may need to stop and get one. So, temperature. You've been learning about this word since who knows when, elementary school. Pretty much you've known that temperature is how hot or cold something is, but it's not necessarily just that. What the actual definition for it is it's the measure of the average kinetic energy. The key phrase here is kinetic energy. Kinetic energy is the energy of motion. So pretty much what temperature is telling you is how fast the particles are moving in that particular substance or area or so forth. So when we say that it's 75 degrees in a classroom, it's actually telling you that your particles are moving fast, but really not too fast, or it would be extremely hot in the classroom. Okay, so what does that mean? Heat. When you hear the word heat, what do you think of? Typically, you think of hot, but heat does not mean just hot. And this is those misconceptions that you need to make sure that you understand. Heat is the transfer, and that is the key word there, is the transfer of thermal energy from one object to another. So for example, me putting my hand on this desk, you can feel like there's some sort of transfer of energy going on because my hand is hotter than the desk. So the heat of my hand is going towards the desk to heat it up, because eventually if I leave my hand there too long, the desk may seem warm there. It's like somebody sitting in a chair for a very long time. They get up out of the chair and then somebody sits down in it and it feels like it's warm because the energy from the original person's who was sitting there has warmed that chair up. Okay, so that's that transfer of heat. Now, why do we associate the word heat with hot is because of how it transfers. The heat always spontaneously flows from the hot object to the cold object. So my hand's energy will spontaneously go towards the desk because the desk is colder. So the energy from my hand is going towards the desk, not the other way around. So when you put an ice cube into water, it's not necessarily that the ice is cooling down the water. It's that the energy from the water is going into the ice cube, melting it. So since the energy is going into the ice cube, that brings the temperature of the water down. Okay, so it's all about that word transfer. It always goes from hot to cold. Now, you should know by now that math is almost a part of everything when it comes to different things in chemistry, and heat being one of them. Heat is represented by the letter Q. I know that it may seem weird, but it is. So it's the letter Q. There are two common units for it, joules and calories. Now you are familiar with calories because it's in food, but actually food calories are kilocalories, okay? Not just plain old calories. But we're going to be using joules in here. So, another definition is law of conservation of energy. We've seen one very similar to this in the past. We've seen law of conservation of mass. It's the exact same concept, but in this case, it has to be in a closed system, because remember, if it's in an open system, energy is declining because of entropy. So in a closed system, meaning nothing can get in or out, energy is neither created nor destroyed during normal chemical activity. So whatever energy you start with is what you have to end with. So in every reaction, in every type of reaction, there's two parts. There's the system, which is what you focus on, which is the actual chemical reaction that's taking place, and then the surroundings, which is everything in the universe. This includes the beaker that it's in, it includes your hand, it includes the whole room, and so forth. Okay, so the system is the actual chemicals that you're looking at. Surroundings is everything else, including the container that it's in. So another vocabulary word is calorimetry. Calorimetry is obviously a way to measure calories, a way to measure energy. Okay, so what this means is that the heat released by the system is equal, so the energy released is equal to the energy that is absorbed in the surroundings. Now this happens because of that law of conservation of energy. It can't just disappear, so it has to go somewhere. So the energy released has to equal the energy absorbed. So what does this mean? This means the Q lost equals the negative Q gained. So they're equal but opposite. So if the system gains energy, that means your surrounding has to lose it because it has to come from somewhere. So what happens is you get two different types of reactions. You get endothermic and exothermic, and their prefixes tell you exactly what they mean. Endo means to go into, thermic means heat. So heat is going into something. So the system gains heat as the surroundings cool down. This means the system absorbs the heat. So the system is gaining that heat. It's going into the system. Exo, exactly what it means exit. Your system loses the heat. So this means your system releases heat. Okay, so endothermic means the system absorbs heat. Exothermic means the system releases it. And if you can remember what those prefixes are, you should be set on that. Okay? So then another vocabulary word. So like I said, I'm throwing a bunch of different words at you here. Specific heat. Now, specific heat is the amount of heat it takes. So amount of heat it takes to raise the temperature of 1 gram by 1 degree Celsius. So how much heat you have to put into something to make the temperature raise. Now, it depends on the substance, because some things when you put it in the oven, you only have to cook for 30 minutes, whereas other things you have to cook for almost a whole day. The reason for that is what substances are making it up, okay? Each different substance has its own specific heat. So for example, air only has a specific heat of 1.01, whereas if we come down to water, its specific heat is 4.18. So this means air doesn't take that much to heat up based on water. Water takes a little bit longer than the air. Okay? So this, you don't have to memorize this chart. You don't have to copy it or anything like that. There is on your reference table specific heats of different metals and things like that. Okay? So the math. This is our equation. Our equation of the day. Q equals mCp delta T. Q stands for heat, which will always be in joules. M stands for mass, which should be in grams. Excuse me. Cp stands for specific heat. Okay? And it has a crazy unit of measurement at the end of it. This triangle T thing, this triangle means change in. So change in temperature. So that means T2 minus T1. Okay? And it will have to be in degrees Celsius, not in kelvins like our gases. So if it has joules, it means it's heat. Grams means it's mass. Degrees Celsius is temperature. So let's try an example. So when 435 joules of heat is added to 3.4 grams of olive oil at 21 degrees Celsius, the temperature increases to 85. What is the specific heat of olive oil? So the 435 joules, there's a joules there, so that should tell you that is our Q, is added to 3.4 grams. Grams means it's mass. Of olive oil at 21 degrees Celsius. It's our first temperature mentioned, so we're going to call that our T1. 85 degrees Celsius is our T2. So one of the first things you're going to do is if you have two temperatures there, that means we need to solve for triangle T first. So you're simply going to do 85 minus 21. So 85 minus 21 gives you 64. Okay, so that's our change in temperature. And it's asking for the specific heat of olive oil. So this means we have Q equals mCp delta T. We need to solve for Cp. So how do we get Cp by itself? We need to divide both sides by m delta T. The m delta T's go away. So you're left with Cp equals Q over m delta T. So now we just plug everything in, solve, and you're done. So 435 divided by 3.4 times 64. Now remember, those parentheses are going to be extremely important. And then you just plug it in. So 435 divided by 3.4 times 64. Based on sig figs, 3.4 is your lowest amount. So this gives you 2.0, and the units for specific heat are joules per grams degrees Celsius. And that's the first example. They are all that easy. No moles are involved, no conversions of any sort. You just plug it in, label and plug. Now, the only catch to it is that you may not always get the numbers that you need in the problem. This is where your reference table is going to come into play. So if you don't have your reference table, you need to have it out. You need the front page of it. Okay, so for example, how much heat is required? So it's asking for Q. What is the Q value? To raise the temperature of 250 grams. So grams means this is our mass of mercury. Now this is going to be important in just a second. 52 degrees Celsius. Now it says how much is required to raise the temperature of 52 degrees Celsius. So this is our change in T already. We don't have to calculate it. So we use our equation. Q equals mCp delta T. Now we're solving for Q. We have m and we have delta T. We're missing something. So why is it important that it's mercury? If you look on the front page of the reference table, you find mercury. In this case, it's right here. And you see in this column here, it tells you the specific heats of the chemicals. So the specific heat for mercury is 0.140. So that's the number that you're going to plug in. So Cp equals 0.14. Okay, so now you just plug and go. So 250 times 0.14 times 52. You don't even have to do any algebra for this one. So 250 times 0.14 times 52. So your answer, based on sig figs, should only be 2. So this is what you get in the calculator, but only 2 sig figs means that. 1800 joules. Okay, so one last example and then we're done. This one doesn't necessarily ask for a number. It asks for identity of a metal. So whenever I ask for the identity of a metal, there's only one way, using the equation that we're using, that can help you do that. And that is to find its Cp. So if you can find the Cp, you can match it up and find what metal it's talking about. So that's what we're looking for. Has a mass of 85.4 grams. So this is our M. 1,430 joules. Joules means that's our Q. To go from 23 degrees Celsius, T1, to 55 degrees Celsius, T2. So again, one of the first things you're going to do is find the change in T. So we're going to do 55 minus 23, which gives you 32. Okay? 32 degrees Celsius. So then, we're going to use Q equals mCp delta T. This time, again, we're solving for the Cp. So how do we get Cp by itself? We're going to divide both sides by m delta T. They go away over here. So you're left with Cp equals Q over m delta T. And now we just plug in. So 1,430 divided by 85.4 times 32. And you should get 0.52 joules per grams degrees Celsius. Now remember, that's not your final answer. The answer is asking for the identity of the metal. So what you're going to do is take this value and compare it to the values on your reference table and match up your answer. So the one that's the closest to it is going to be titanium. 0.52 equals titanium. So your answer is that. Okay, so literally just label, do some algebra every now and then, plug in and solve. If you have any questions, please bring them to class.